So of course we have an ideal in a polynomial ring, but the point of one point of an ideal is we can form a quotient ring, right? So we can either speak about the ideal or we can speak about the quotient ring. And for the ideal there's usually an adjective, and for the quotient ring there's a noun. Okay, so if I, for example, is a maximal ideal, then the quotient ring is a field. Okay, very good. Quotient ring is a field. If I is a prime ideal, then the quotient ring is integral domain. Okay, so it's called integral domain, or just domain. Okay, so those are the same, they're equivalent. So, I mean, you can do other things. If I is a radical ideal, then the ring is a reduced ring, and so on. Okay. Now, an integral domain means there are no zero divisors. Well, a polynomial ring is an integral domain because the zero ideal is prime, right? But if you have a subring of an integral domain, then it's also an integral domain. Okay, so a basic fact is that every subalgebra of a polynomial ring is automatically an integral domain. We're going to use that in a minute. Okay? So now I'd like to address the question, how can you show that a variety is irreducible? Or perhaps a little harder, how can you show that an ideal is a prime ideal? Okay? Now these are hard problems. So computationally these are not easy problems. These are difficult problems. And we will learn some tools in this course to address them, but this is, not snake. I'm not selling snake oil. I mean, this is, we're trying to do what we can, okay? But I'm trying to give you the language to talk about these problems. So for K, for example, he says, I have a whole bunch of polynomials, of degree 18 and 16 variables, and I think, my variety is irreducible. And maybe if I'm lucky, it's prime or not. Okay, so maybe my varieties are. I said, I believe you, right? So then, how should we speak about this? What tools, should we use to address this kind of question? Okay. So here's the first fact. Now, a conclusion corollary to this fact is the following. Suppose I could write an ideal P as the kernel of a ring homomorphism between two polynomial rings. So somehow, I can make, and now I'm going to write K for a field, but could still be a rational number. So I have a polynomial ring in n variables. I'm mapping it to a polynomial ring in d variables. Well then, P is automatically a prime ideal. And if P is prime, then the variety is irreducible. Okay? So if somehow, right, so first of all, why is it true? Well, let's think about this. This is, I think it's called the second isomorphism theorem in undergraduate algebra, right? So you learn this for groups and rings and stuff like that, right? So one of the undergraduate algebra isomorphism theorems says the following, right? So we have a homomorphism, right? So then, if we take this one modulo the kernel, then it embeds in here, right? So the polynomial ring, so if P is the kernel of this map, then the polynomial ring in n variables modulo P embeds as a subalgebra a polynomial ring in d variables. But that means that this thing mod P is an integral domain by this fact. By this fact it's an integral domain, and by the yellow quiz over there we conclude that P is a prime ideal. Okay? So if you have an ideal, if you can somehow argue it's the kernel of a ring homomorphism given to you by n polynomials in d variables, then it's automatically prime. Okay, so let's see what we can do with this. Okay, so I'd like to prove that the set of m by n matrices of rank at most r is an irreducible variety. Okay, that's a variety. So very often you're given some linear algebra problem and you want to show that something is an irreducible. This is a very easy one. We're going to go over that. But you can make it harder, right? So in Hong Kong you could ask, let's take the set of all tensors that have an eigenvector in a given linear space. You get this? Right? Take the set of all tensors of a given size that possess an eigenvector inside some given linear subspace. That's some set, right? Some person applications might be interested in that. And we might want to know, is this an irreducible variety? What techniques do we have? So let's do it for this linear algebra problem. Okay, so proof. So X is our matrix. So we know that a matrix over a field has rank at most R if and only if X admits a low rank factorization. So X can be written as a product of a matrix Y that's tall and skinny and a matrix Z like this. So this is an M by R matrix and R by N matrix. Okay, it's not unique. This is never unique, but there's some, that's what it means to have rank at most R. Okay? Well, but this kind of factorization we can then translate into a ring homomorphism, right? This is a parametric representation of low-rank matrices, so this translates into a ring homomorphism. So let P be the kernel of the corresponding ring homomorphism. Of the ring homomorphism, so we take the polynomial ring Kx. So by this I mean the polynomial ring in m times n variables, the entries of the matrix X. And then there's a homomorphism into a polynomial ring Kyz in Rm plus Rn variables. And the homomorphism is simply, Xij maps to the sum L from 1 up to R, YIL, ZLJ. Okay? So we have a forward map. So in algebraic geometry, we have a forward map of affine varieties. Right? We have a map from YZ space into X space. And the object we're interested in is the image. Or maybe the closure of the image, right? But this happens to be closed, okay? But the image from this map, the geometric map from YZ space into X space. At the level of ring of functions that's contravariant, the map goes the other way. So at the ring of functions, we have a homomorphism from the polynomial in the X's back to polynomials in the Y's and Z's, and this is the homomorphism. So I just tell you what it does in the generator, and that uniquely determines this as a K-algebra homomorphism. Okay? Well, then, so P is, so this implies that P is prime. And therefore, the variety of P is irreducible. Okay? And if you unravel what I said, well, the variety of P is exactly up to closure. Up to closure is exactly the set of matrices of rank at most R, right? So the variety of P is the set of all matrices that admit such a factorization. Voila, that's it. Okay? Now, we don't know what P is, right? We have no idea at this stage, what P is, right? So this is the set of all matrices of rank at most R. That's an irreducible variety. Same thing for tensors, right? Or for any other situations where we have a notion of rank, a reasonable notion of rank. The set of all things of rank at most R is an irreducible variety because it's defining radical ideal as a prime ideal, and I have realized that prime ideal as a kernel of a homomorphism between two polynomial rings. Okay? Is that argument clear? Okay, now let's go a step further. Now we can ask the question, what is P? Right? So this tells us in our triplets problem that, the variety of all matrices that can be factored as a product of two triplets matrices, it's an irreducible variety. And so it's given by some prime ideal. Right? So what that prime ideal is a difficult problem, so that we don't know yet. But let's, in this case, in this example, it's of course known. It's what you think it is. And let's spend a little time with the following theorem. Okay, so the ideal, let's call it I, generated by the R plus 1 times R plus 1 minors of a matrix of unknowns Xij is a prime ideal. Okay, so I'd like to tell you a little bit about the proof. Okay, so how would you prove this? So I'm looking at a polynomial ring and m times n variables, xij. I look at all the minors, the r plus 1 times r plus 1 minors. And you can, again, this is a scale, you can replace this by other situations. You can replace minors by Pfaffians or pentads or, whatever, things like that. Okay? So I take the minors of a given size, and I claim they generate a prime ideal. The quotient by that is an integral domain. Okay, well, let's get going. So here's how I would argue. Okay, so first of all, we know that the variety of I, which is the same as the variety of P, is an irreducible variety. And over the algebraic closure of K. So let's assume K is algebraically closed. Okay, so the variety is an irreducible variety. It's the variety of matrices of rank at most R. So I'm appealing to undergraduate knowledge, right? You know that a matrix has rank at most R if and only if the next size minors vanish. Okay, so I have this ideal I, right, that I know, and it cuts out the correct variety, and that variety is irreducible. But then there's this unknown prime ideal. There's this mysterious prime ideal that I don't yet know. Okay? So the goal somehow is to show, right? So I want to convince you that I is P. Right? Okay, that's what we want to get to. But let's go one step at a time. So we're going to use the Nullstellensatz, the theorem of zeros. It says that the radical of I is equal to P. Right? So if two ideals, I and P, cut out the same variety, then algebraically they have the same radical. But P is prime and hence radical. Right? Because every field is a reduced ring. Right? So if P is, every integral domain is a reduced ring. So therefore, we know that the radical of I is P. Okay? Hence, it suffices to show, so I'm going to show that the initial ideal of I with respect to some term order is square free. Okay? With a lemma 55 minutes ago that says if an initial ideal is square free, then the ideal is radical, right? But if I can show, that I is radical, then I is equal to P, right? If I is equal to its radical, so all I need to show is that I is radical. And I'm going to show that to you by showing that in some term order, the initial ideal is square free. I'm going to use the earlier lemma. Well, let's do it. So here's the key lemma. This will imply everything. So the key lemma is that the minors of a given size, so the r plus 1 times r plus 1 minors, form a Grobner basis. Okay? Suppose I could show that. Suppose, I find some term order that makes this a Grobner basis. Then I'm done. Right? Why is that? Well, the minors, they're just determinants. Every term is square free. Right? In the expansion of a determinant, every monomial is a square free monomial. Okay? So whatever the term order is, if these guys are Grobner bases, whatever the leading terms are, right, the leading terms will be square free. By the Grobner property, they generate the initial ideal, so the initial ideal is radical. So therefore, I is radical, blah, 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 blah. Okay? So this lemma will imply everything. So if I show that the minors form a Grobner basis, then I get that P is a primer. Now, how do you prove this? Okay? So now, proof. Okay? So, well, it's no free lunch. Even next Friday at my undergraduate lecture, the lunch is not free, but almost. It's 1,001. Okay? So, but there's no such thing as a free lunch. So, not so easy. Okay? Not so easy. Okay? So, let me do an example. I'm going to prove it to you in one example. There are basically 2 or 3 proofs. I'm going to tell you briefly what they are, but let's do an example first. I think it's instructive to see an example. Let's do a very small example. Okay, so my example is M is 2, N is 3, and R is 1. Okay, so A, B, C, D, E, F. These are matrix entries. Okay. So I said yesterday, it's always good to pick meaningful entries for a matrix. And that depends what you want to do. If you want to make a small calculation, it's best not to use indices. So somebody yesterday struggled, to automatically, get Macaulay to do double indices and so on, and they didn't get to actually doing the problem because of that, or was slowed down. So sometimes it's good to call the matrix entries A, B, C, D, E, F, G. Okay, and you're ready to go. Okay, so what are the minors? Well, so I'm going to pick a term order. So AE minus BD are the minors. AF minus CD, BF minus CE, and I'm going to pick a diagonal term order. So I make these the leading terms. So every 2 by 2 minor, there's a diagonal term and an anti-diagonal term. And if I tick I order the variables row-wise and then lexicographic, then the underlying terms are the leading terms. Okay? So now I claim that this is a Grobner basis. Okay? So, well, what do? You have to check all the S pairs. So let me remind you how you check that something is a Grobner basis. So you pick any S pair. Okay? So for example, you take this S pair and you multiply this by F minus this by E, right? So the leading terms cancel, so you get C, D, E minus B, D, F. Okay? So I have to show you by Buchberger's criterion that the S polynomial reduces to 0 under the division algorithm, and it does, right? So this is simply a multiple of that one, right? So you do the division algorithm, for example, you take you take this one, BDF, right? And you replace B times F by C times E. That's one step in the division algorithm, and you get 0. Okay, so the S pair between these two is 0. And by the same symmetry, the S pair between these two is 0. Finally, this one is even easier, right? The S pair between these two is automatically 0. That's Buchberger's second criterion, right? If you have relatively prime leading terms, you don't have to check anything. Okay? So that's automatically 0. So if you have two polynomials and the leading terms are relatively prime, the S pair will go to 0. Okay? So we just checked Buchberger's criterion. Okay? So this is just a direct proof. So check by Buchberger's criterion. Okay? Well, maybe we can carry this a little further. So let's do, a matrix of size 2 by 1000. Okay? So let's see whether we can use the same argument. Okay? So I still take R to be 1 and M to be 2, but now 1 is 1,000. N is 1,000. Okay? So, well, the same argument still works, right? Take all the 2 by 2 minors, right? So you have 2 by 2 minors somewhere in the matrix, right? Well, if they don't overlap, if they have no variable in common, then, Buchberger's second criterion, the S pair will go to 0, right? If they do have a variable in common, they sit in a 2 by 3 block. But I've already done the 2 by 3 case, right? So I can make the rows longer. Right? So I can get some mileage out of this kind of argument. Okay? So there are basically, two approaches. So let's call this directly, brute force Buchberger. And there's a proof. Okay? So there's a proof that does exactly that. So you take the minors of a given size, of m by n, and you can reduce to the case where m and n are at most 2r minus 1, right, by this overlapping argument, right? So you only have to look at minors that sort of share something in common, and m and n are small compared to r, maybe 2r minus 1, right? And then you do it, right? Then you see how they overlap, you classify all the cases where they overlap, and all the S pairs go to 0, and that's a 35-page paper. Okay? So that's the theorem. Okay? So that's one proof. Now there are other proofs. So now I was once involved in a proof, and the paper is actually very short, and I don't want to praise myself. I want to praise somebody else now. Okay? This was a long time ago. So this when I was a postdoc. In my very, very first year as a postdoc, I was very, very, very young. And I had a conversation with Bruno Buchberger about this. I said, Bruno, do you think the minors form a Grobner basis? And we discussed. And anyway, so I had this conjecture, and I wanted to prove it. But I didn't know anything. I didn't know any algebraic geometry. Remember, in Darmstadt, we didn't know any rings, right? So I didn't know a lot of algebraic geometry. So I tried this. But I'm the world's most impatient person. So I could do that case, and then I realized I can't do this. Okay? I couldn't do this. Okay? Now here's another way to prove that something is a Grobner basis. Okay? Suppose I know the Hilbert function of the residue ring. So here's my, ring. So let's say, this is the true, ring. So this is the algebra generated by the product y times z. Okay, so that's the true. This integral domain is kx mod p. I'm sorry I'm telling stories now, but I think it's a good story to tell. Okay, so I knew the Hilbert series of this ring. So I knew how many. If I only knew a Grobner basis, I knew how many standard monomials to expect. Okay. And the reason I knew that, there was a brilliant, wonderful senior combinatorialist with whom I had the pleasure of interacting at the time, Giancarlo Rota, and he was very interested in combinatorics and invariant theory. And from him, I knew the Hilbert series of this ring. Okay? I said, well, here's another way to prove the Gröbner basis property. So I said let's take the diagonal terms, we're going to take the diagonal leading terms, so xi1, j1, xi2, j2, up to xir, jr. So this is, I'm interested in this monomial ideal where I1 blah 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 less than jr, j1 up to jr. Right? So these are the diagonal leading terms. So I'm interested in this monomial ideal. If I can show that this ideal has the same Hilbert function as the true ideal, then I'm done. Okay? Now why is that? Well, this is, whatever this ideal is, it's certainly contained in the true initial ideal. Right? So I have this true, oh, now it's I, right? So, okay, P. Okay, so I want to show that this is a Gröbner basis, so I is the ideal of minors, right? So certainly these are among the leading terms, so these terms are among the leading terms. But maybe there are more, I don't know, right? But here's the thing about graded algebra. So if I have, an ideal sitting inside another ideal, and in every degree they have the same dimension, they're equal. Right? So if I could show, so I know this Hilbert series because I know the Hilbert series of I by Rota, right? But I don't know the Hilbert series. If I could calculate this Hilbert series and show they're equal, then I'm done. I said, okay, well, how hard can this be, right? This is, square free, so I was ready to go. I said, well, I draw my matrix like this, and this is a poset, right? So I look at standard monomials, right? So what's a standard monomial? Well, it's a collection, of monomials that, doesn't contain, it's a standard monomials that are square free. They lie in at most R chains in this poset. So this has something to do with chain decomposition of posets. So, okay, and then based on this, I got some combinatorial formula. Okay, so now I had two combinatorial formulas. I knew combinatorially, this Hilbert series, and I knew combinatorially that Hilbert series, but I didn't know whether they're equal. Right? I tried some examples; they were always equal. And after playing some more, in the end, all I needed was a bijection. Right? I had some combinatorial set here that counted standard monomials. I had some other combinatorial set there, and I needed that they were in bijection. And I had no idea how to do it. Okay? So then I met Anders Björner. So this is now an advertisement for FPSAC. Okay? So FPSAC is a conference in enumerative combinatorics next year in Dijon. Right? Please all come. And I said, Anders, I have this set, and I would like it to be in bijection with that set. And it was one of those lucky moments. He said, of course they're in bijection. Everybody knows that. That's the Knuth, Robinson, Shenstedt correspondence. Okay? So that was my paper. Okay? So he helped me out, right? So I was looking for, I had no idea how to do it, but this other people had done it before me. So that's a well-known correspondence, a bijection between two things, and that's the proof. Okay. So there are many roads lead to Rome. So there are many ways to prove that something is a Gröbner basis. Sometimes the Buchberger criterion will do it, sometimes the numerical calculation will do it. But in highly structured situations, some knowledge of combinatorics tends to be a good idea also. Okay, now I wasted a lot of time. Let me go back to the lecture. So anyway, the minors form a prime ideal. Let me digress one more time. So the undergraduate lecture next week is on tropical math, right? So the minors form a tropical, they form a Gröbner basis. Here's a question, do they form a tropical basis? We'll come back to that. So I'm not going to give you the definition of tropical basis, but you know the definition of tropical basis. So if you want to know the definition of tropical basis and whether the minors form a tropical basis, you speak to him. Okay? Okay, let's continue with the lecture. So question. If this works fine for determinants, how about permanents? Okay, so let's take the R by R subpermanence of an M by N matrix. So what's a permanent? Wherever you see a minus, you replace it with a plus. Okay? Now computer scientists and the field has characteristic different from 2. Okay? So the permanent is actually different from the determinant. Computer scientists really like the permanent because it's hard to compute. So determinants are easy to compute, permanents are hard to compute, and if you can somehow show that the permanent isn't really a determinant, then P is not equal to NP and you win a lot of money and glory. Okay? So computer scientists really like permanents. And so you can play with this. And if you read, it's a nice example. I think these are very nice examples for primary decomposition. If you read section 5.4, you can find out quite a bit. So let's do one example. Let's take this matrix, let's take a 2 by 3 matrix, and let's take the 2 by 2 subpermanents. So AE plus BD, AF plus CD, and BF plus CE. And as I said now, K is a field of characteristic different from 2. Well, this example, this ideal is radical. It's not prime. So the determinants generate a prime ideal, but this one is not prime. It has 5 primary components. So A, B, C, D, E, F, AE plus BD, CF, AF plus CD, BE, and BF plus CE is AD, okay? And that's it. So it's the intersection of 5 primes. So again, all the associated primes are minimal, and therefore the primary decomposition is a unique prime decomposition. And what does it mean? Well, how could the 2 by 2 subpermanents be all 0? Well, if the first row is all 0, case 1. Case 2, if the second row is all 0, right? And then the other cases is if a column is 0, right? So a column could be 0, and then the remaining 2 by 2 permanent is 0, okay? This has codimension 3. So there are 5 degrees of freedom in making a 2 by 3 matrix, all whose permanents are 0, okay? And one of the exercise problems, is about the permanent. The permanent is a good polynomial to play with, okay? So that's the permanent. So this is a complete intersection, codimension 3. I'm going to say something about this. Okay. This is a nice case, if you make the matrix longer, right? So if you take the permanence, you make the matrix for 2 by n matrix. There's always a radical ideal and complete intersection, and the number of associated primes is the Fibonacci number. Okay, so if you're a combinatorialist and you hear the number 5, there are two things to think. It's either a Catalan number or it's a Fibonacci number. Okay? In this case, so last week it was a Catalan number, now it's a Fibonacci number. So, right, so the number of associated primes, if you do this for a 2 by n matrix and you ask, then it's a Fibonacci. Okay, so what else? Let me give you 2 more useful results about primary decomposition. Okay. So here's the result. Suppose I is a binomial ideal. And now, just for the purpose of this discussion, let me pick the coefficients to be the complex numbers, just for the moment. Okay, so I have a polynomial ideal in n variables, and it's a so-called binomial ideal. So what's a binomial? What's a monomial? A monomial is a polynomial with one term, x1. Well, that's a monomial, and sometimes we allow a coefficient. Okay, so we call that a monomial. Okay. Now a binomial is if you take two of them. Right, so a polynomial with at most two terms is called a binomial. Now here C or D could be 0, so it's allowed to be a monomial. Right? So, and a binomial ideal is an ideal generated by binomials. Okay. Now in the world of ideals, from this perspective, there are sort of three kinds. First of all, there are the monomial ideals, right? And they are very, very, very easy, right? So if you read this undergraduate book, we know everything about monomial ideals. Monomial ideal, the radical is monomial, the primary decomposition, everything is monomial. Everything is super, super easy for monomial ideals, okay? Everything is really difficult for general ideals, but right in the middle are the binomial ideals, okay? So binomial ideals are special, and the theorem says if I is a binomial ideal, then all the operations we discussed today stay in the category. Then the radical of I is binomial. Every associated prime is binomial. And I admits a binomial primary decomposition. Okay, so there exists a primary decomposition where every primary ideal is a binomial ideal. Okay, so everything is binomial. Okay. Now, the same statement holds for monomials. Same holds for monomials. And that's, for example, in the Cox-Lochet book, but certainly not for trinomials. It cannot hold for trinomials because trinomials are universal. Every variety, every scheme, every ideal can be written in terms of trinomials. Okay, so you look puzzled. Well, suppose you have some bunch of polynomials, a polynomial system with lots of terms, and maybe there's a polynomial, that has 4 terms, like this: a plus b plus c plus d. Okay, what you can do is you can introduce a new variable, z, and can replace this by a plus b plus z and c plus d minus z. Okay? So whenever you see a polynomial with 4 terms, you can replace it by 2 polynomials with 3 terms. You add a variable. Okay? That doesn't change. It adds more variables, but as far as the quotient ring is concerned, that doesn't change the ring. Right? So it changes the ideal, but the ring stays the same. So every ideal, in this sense, can be expressed by trinomials. So trinomials are universal, okay? And that's a hard problem. But binomials are special, okay? So this is a question.
Why does that imply that this cannot hold for trinomials if everything is trinomial?
No, okay, yes. So it's also true. Well, yeah, you can have a.
You have to add variables.
Yeah, you have to have exactly. So. You can certainly have okay, so let's talk a little bit about, here is the Fermat curve. So this polynomial is irreducible. Oh, I guess that's a bad one. Okay, so. Yeah, okay, whatever. So, in any reasonable sense, so what I'm saying is trinomial is a universal. So the binomial, but binomial is special. So So these primes are all toric ideals. So if you have a binomial scheme, then you decompose it into things. So this is a theorem that was proved in a paper with Eisenbud in maybe 98, so Eisenbud and myself. And in the meantime, this has been further developed. So there are many algorithms that specialize in this case, and they're quite fast. So if you have a situation that's a binomial situation, then you can do primary decomposition. You can all do that in a purely combinatorial way. So there's a combinatorial theory of primary decomposition that stays in the category. And this is something you want to recognize. So for example, when you talked yesterday about the ED degree of the Fermat hypersurface, right? So basically the equations were like this, right? So you had a whole bunch of equations like this, and then let's forget this for a moment, right? So whenever you see something like that, you go binomial primary decomposition. So you apply this theory, and you have a very nice description of the components. Okay? So as soon as you see binomials, you want to recognize that structure. Okay? The second useful theorem, and there's a package. So for example, in Macaulay 2, Thomas Kahle, there's a Macaulay 2 package for binomial primary decomposition. So if you type in a binomial ideal and you apply the general primary decomposition code, it will not terminate. But if you apply the special package, for binomial primary decomposition, it will go quite far. Okay. So the second theorem I wanted to mention pertains to this example. It's also very, very useful. It's a classical theorem in commutative algebra, and that's called Macaulay's unmixedness theorem. So in the book I'm loosely following, that's theorem 5.7. And it says the following. So Macaulay was a person. Okay, so the software, so in this community what people do, they name their software after people. Okay, so Macaulay was a person and Bustini was a person and so on. Okay, so, and he proved the following theorem. So if I is a complete intersection of codimension C, then I has no embedded primes and every minimal prime has the same codimension. C. Okay, that's Macaulay's unmixedness theorem. Okay, that's a very, very useful theorem in practice. Okay, so for example, let's look here at our 2x2 permanents. Okay, so how to do this? So I claim we can see, how can we see that? Maybe I'm lying right now. Okay, so I claim, here we can see this is given by 3 equations and the codimension is 3. Okay, so it's a complete intersection. So therefore I know ahead of time that all associated primes are minimal. There are no embedded primes, and all the minimal primes have the same dimension, 5, 5, 5, 5, 5. So unlike in the previous example where we had, the product of two by two matrices, we had no different dimensions, right? We had 4, 4, and 5, right? So this cannot happen if you have a complete intersection. So Macaulay says if you know for some reason that you have a complete intersection, things are always this nice. Very, very useful theorem. And then you can get numerical information, so a corollary to this, 5, 8, and here let's assume that the ideals are homogeneous. Then the degree of I, so degree is whatever Macaulay 2 produces when you say degree. So this is the leading coefficient, the normalized leading coefficient of the Hilbert polynomial. This degree is the sum from I from 1 up to R, degree of Qi. The degrees add up. So in this case, 8 plus is 1 plus 1 plus 2 plus 2 plus 2. Okay, so it's a complete intersection of 3 quadrics. So the degree is 8 by Bezout's theorem, 2 times 2 times 2. And I know ahead of time by Macaulay that I will have components of degree 1 plus 1 plus 2 plus 2 plus 2. So this kind of degree information is what Bertini will give you if and when you calculate irreducible decompositions in Bertini. Then this is very, very useful information. Okay, so those are the theorems I wanted to state. So I have a few more minutes for questions and philosophy. So are there questions?
What's the dimension of the R plus 1 minus?
Pardon me?
The zero set of the R plus 1 times R plus 1 minus?
What's the dimension?
Yeah.
Ah, okay. Well, there are various ways to see this. So in this case, the naive count will do it. So suppose I have a matrix. It's an M by N matrix. So what's the degrees of freedom? How can I make a rank R matrix? Okay. Well, I can certainly take the first R rows and fill them with arbitrary numbers. Right? So I can fill the first R rows with any number. So I certainly have those R times N degrees of freedom, and the other rows I take linear combinations. Okay? But I can do better. I can also, in addition, fill the first R columns with arbitrary numbers. Right? And I claim I can still fill this up to a rank R matrix. But this is the best I can do, because as soon as I put in any other entry, then I have an R plus 1 minor that gives me a constraint. So the dimension of this determinantal variety is what comes from this argument. So it's MR plus MNR minus the overlap, which is R squared. A better argument is to calculate this with the leading principal minors, with the leading terms of the minors. So if you take the diagonal terms of the minors, okay, we have to find a largest set S of the variables such that every subset in those variables is standard. Think about my chain decomposition, right? So what this says, we're looking for subsets of this poset, this product of two chains that contains no anti-chain of size R plus 1. And that's the largest set. Okay, so the combinatorial definition here has to do with the subsets that don't contain an anti-chain of a given set. Okay, so that's the answer. So, other questions?
Is that also a Grosvenor basis?
I think no, actually. Can you check it, please? Would you mind? So, I was just going to say it is a Grosvenor base, and then I caught myself lying. Okay, so a little bit about philosophy. So let me say a word about this project. So it was very funny. So when we started this paper, so people make mistakes. Okay, so in the first manuscript, okay, we put K, and we said K is an algebraically closed field. Okay, so we stated everything, for an algebraically closed field. Well, you certainly need algebraic closure, right? Because you certainly need algebraic closure, or something like algebraic closure, right? Because if you have, I don't know, let's say we're over the field of real numbers. Here's a binomial ideal over the field of real numbers. It's radical, so it has unique, decomposition, but the decomposition is not, into binomial ideals. So it certainly falls over the field of real numbers. Okay? But it's true over the field of complex numbers, right? So over the complex numbers, you're okay again. You put a root of unity, And okay, so you can see roots of unity, right? That will do the trick. Okay, so we're okay over the complex numbers. Then we stated the theorem, it's going to be true over an arbitrary algebraically closed field. Okay. Now, it's actually not so bad, right? Even if you're in so suppose you're in characteristic 3. Suppose we have an algebraically closed field in characteristic 3, then, this is primary. It's not prime, but it's primary. And you can sort of argue, you make a little argument, maybe characteristic 0. So maybe we forgot what I was saying. No, I have this ideal, but the radical is still, binomial. So the ideal is binomial and the radical is binomial. Okay? So everything is okay. And then somebody found a counterexample. Okay? So it turns out the field has to be perfect. Okay? So you need it's a perfect field. So is this true? For an algebraically closed field, that's perfect. Okay? Now, until that day, remember my technical school, I did not know what a perfect field was. But from that day on, I knew what a perfect field was. So it's true, K has to be a perfect field. So if you have in characteristic P one of those crazy fields that's not perfect, it's actually not true. Okay? So that's one remark. Now here's another thing. Sometimes, let me change. I want to make one more remark and then I shut up. So, why do we care about non-radical ideals at all? Right? Let me play devil's advocate. So let's say I'm Matt, I'm a Bertini developer, I say, I don't care about all this non-radical business, all this embedded stuff. All I care about is varieties, right? All I want is solve polynomial equations, right? And from that point of view, I don't care about radical or not radical. So let me make an argument that counters that. Okay? So what does an ideal represent? So suppose I have an ideal in a polynomial. Okay? Let me call the variables d1, d2 up to dn. Those are just the names. I can choose variable names any way I want. Okay? Well, of course, it represents a system of polynomial equations. I want to calculate the zeros. Okay? But really, it also represents a system of linear partial differential equations with polynomial coefficients and with constant coefficients. Sorry, that's another story with constant coefficients. Right? That's the same, right? That's a system of linear PDE with constant coefficients. You can solve the PDE, right? But now, radical or not radical, or schemes make all the difference. So if a student asks me, why should I study schemes rather than varieties? The answer is because schemes are solution sets to systems of linear PDE. And I'm going to give you one example, and then we take the lunch break. Okay? Let's take a very simple example. Let's take n equals 1. And let's take at the following ideal. Delta squared, that's my variable. And then let's put minus, is that what I want? Yes, let's put minus epsilon squared. Okay? So epsilon is a small number, like 0.0001. Okay? Let me look at this ideal. Okay? So what are the zeros? Okay, so there's two solutions. So the variety, right, has two solutions, epsilon and minus epsilon. Okay? We agree, right? That's the variety. Okay? But let's look at this from the point of view of PDE, right? So this is an ODE, right? So this represents the differential equation. So we're looking for an unknown function, f, in one variable, such that the second partial derivative is epsilon squared times f. Okay, so we're interested in solving this differential equation. Okay, so it's a linear differential equation. So the set of solutions are not those crazy wiggly set that Paul Rabinovich drew yesterday, but it's a linear space. Okay, it's a linear space. Okay, Well, what's the dimension of this linear space? The dimension is 2, right? It's a constant coefficient second order ordinary differential equation. So the solution set is a 2-dimensional space. And we can write down a basis of entire functions that solve this. So everybody knows this. So this we certainly learned in the engineering school, right? So you go exponential of epsilon x and the exponential of minus epsilon x. And you can write it in sine and cosine, right? So that's certainly that's a basis. Okay, so these two functions span a 2-dimensional solution space, and that's the solution, right? So if I is a radical ideal, a 0-dimensional radical ideal, that's the answer, right? You just take the roots and you make the corresponding exponentials. You learn this, right? Now let's make epsilon small. Okay? Now, epsilon goes to 0. Okay? Now what happens here? Well, if epsilon goes to 0, the variety is just a single point. Right? We had 2 roots, but they come together, right? So those of us who don't believe in schemes, 2 points became 1 point. That's okay, right? The origin is now a root. What's the solution set? Well, for epsilon equals 0, right? So for epsilon, we're interested in functions whose second partial derivative is 0. Right? So that's a 2-dimensional space, right? That's spanned by constant functions and the function x. Right? So from the point of view of differential equations, nothing changes, right? For every value of epsilon, I have a 2-dimensional solution space. Right? And in fact, I can adjust the basis that the basis moves along, right? It's a vector space. I can choose my basis. I don't usually do that, but I could if I wanted to. I could replace this basis by, how about here I keep this one, and now help me out. So I'm going to take a half of the first one minus the other guy. Okay? And now as epsilon goes to 0, right, this basis vector becomes this basis vector, and this basis vector becomes this basis vector. Okay? So I have a perfectly good family, flat, as algebraic geometers would say. I have a perfectly good vector bundle. Right? I have a 2-dimensional space all across the epsilon line. Okay? So nothing changes. The only thing that changes is the nature of the solution, right? So here we have sort of exponential growth, and here something special happens. And that's why you should always keep the ideal and not just replace it by its radical. We will meet at 2 o'clock. We hear from Michael and from Youngbin, and then in the afternoon we'll practice some more, decomposition.